Hi, good morning. Now I want to introduce Gauss's law and talk a little bit how we are going to calculate the field. Now we are going to know that Gauss's law, it is an alternative method to calculate electric field. And actually it is mostly used with continuous distribution of charge, which means, let's say you have a rod or sphere or a sheet that has charges on it. One thing that really I will say here for Gauss's law, it's not going to be, I will say, a general principle. It has to do with symmetry. Then when we have symmetry, we will be able to use it. If we don't have that symmetry, it's going to be very difficult to use it. Now, before we start with this, we need to define something called electric flux, because this is part of the formula. Now, the electric flux, it is like any field, is going to be having, a surface. And as if I am looking at like how many lines of the field are going through that surface. Actually, we use for calculating electric flux, we call it phi, E times A, and then cosine phi. Now that angle phi, it is the angle between E as a vector and the normal to the surface. Then if I will say, my surface is in like this here, and this is the normal for the surface, and let's say the electric field, it is this way, then here phi is 0. And with phi 0, we're gonna find that cosine phi is gonna be cosine 0 equals 1. And then here I'm gonna have like all the lines, they're gonna hit the surface perpendicular, and this is gonna be the maximum flux. And of course, E here is going to be the magnitude of the electric field. And A, it is the area. And the area, of course, should be in meters squared. Always we can say that the electric flux has to do with like how much of that electric field it is perpendicular to the area. I'm gonna solve one example here related to Gauss's law. Okay, calculate the electric flux through a disk with radius 0.1 meters. The disk is oriented with its axis, which is the one that which is normal to surface at an angle 30 degrees to a uniform electric field with magnitude to 10 to the 3 Newton per Coulomb. Now I will calculate, okay, when it has this orientation, and here I will maybe have just a diagram that is gonna be E, okay, and the disk is like kind of sitting somewhere here, and that the axis through, let's see, I need to add more lines, and that the normal here, let me use another color, this is 30 degrees, and the radius R, it is 0.1 meter. First area, it is pi r squared, and it is pi 0.1 meter squared, and the flux, it is EA times cosine phi, then it is the 2 10 to 3 times pi 0.1 times cosine 30, and that is going to give us 54 Newton times meters squared divided by Coulomb. Also, we can repeat the calculation when the disk is turned so that its plane is parallel to E. What is the total flux through the disk if it is turned so that its plane is parallel to E? And that is gonna happen, okay, like this. This is E, and the disk is gonna be sitting like this, and its axis is gonna be this way. Now here, phi, it is 90, as you can see, and then the flux is 0 because cosine 90 equals 0. Now we can also find another case, which is number C, and that is when the disk is turned so that its axis is parallel to E. And here is going to be this case. Like it's going to be like, the disk is going to be something like this here. And then the area vector for it, or its normal, is going to be in the same direction. And here phi is going to be 0, and then this is going to be EA times cosine 0, which is 1. And this is the maximum flux, and that is going to be 2 10 to 3 times the area. And that is the maximum flux that we can get for this case. Okay, this is just introducing the electric flux. Thank you.